So the next topic is distributions of data. The simplest way to think about a distribution of data is just the shape of a histogram. So let's look at a few histograms. And let me just zoom out a little bit. Too far. All right, so here's one I have, for example. Let's suppose that somebody that plays basketball has a 75% free throw percentage. So anytime they get up to throw a free throw, there's a 75% chance it's going to go in. Okay. What if they were going to take 12 shots? What's going to happen? Well, usually they would get 75% of those 12 shots in, and that would be 9. Now, it's pretty rare that they would get none in. That's not going to happen very often. Now, they could get all 12 shots in, but that's not going to happen often either. So this right here is the distribution, probability distribution of how many shots a person with 75% chance on a free throw, how many they will get in out of 12. So what I can see about this distribution, it's got this nice hump over here, kind of bell-shaped. And then it's got this very narrow tail, right? The probabilities in my chart are so small, I can't even see them right here. If I showed more decimal places, they would exist, but it's pretty small. So just for fun, on a couple of those zeros, if I ask the computer for more decimal places, I can see that there is a possibility. It's just very small, right? 0.0000001%, right? It's not going to happen very often in someone's lifetime if they're that, 75% chance. Look at this one right here. The chance of getting only 5 out of 12 in, right? They miss the other 7. They get 5 in. That's unusual because they usually get 9 out of 12 in. 75% of 12 is 9. So we can see that should only happen about 1% of the time. They'll get 6 in about 4% of the time, and 25%, that's the highest percentage here, they'll get 9 shots in 25% of the time. Distribution here, we would say this is skewed to the left because it has this left tail. Let's look at another one. If someone had a 50% chance of getting in a free throw, half the time they throw it, it goes in, half the time it doesn't. If they took 12 shots, we would expect, though, most of the time, more often than not, they'll get about 6 out of 12 in. So if we look at the probabilities related to that, how I calculated these is a whole nother story, and let's not worry about that. But 6 right here in the middle has the highest probability. Notice it's got the highest stack here when I click on that, right? Almost 23% chance of getting 6 out of 12 in, right? So let's not confuse the 50% with the other percentages here. 50% is the chance of 1 shot going in. But this person is doing 12 in a row. Half the time I'll get them in, half the time he won't on average, right? That makes the 6 more likely. This distribution right here of possibilities is perfectly symmetric about the middle, which is 6. Is it possible they could get none of them in? Sure, that can happen. Like flipping a coin, you could get heads 12 times in a row. It's not going to happen often, but it can happen. So this distribution right here, I would say, is symmetric. It also has this kind of bell shape to it. So let me just demonstrate that. Hang on one sec. Oops. Come on, I'm trying to get a screenshot. There we go. And current page. Oops, I grabbed the Zoom stuff in there too. Ooh, that's weird. Okay, screen's being funky. All right, ignore that zoom thing in there. Sorry about that. So when I'm thinking about a distribution from a histogram like this, I'm kind of squinting my eyes and blurring it and imagining a line going through the tops of these right here. So if I were to draw a line through the tops here, it's more curved and looks like this. Okay, so this is the symmetric bell shape I'm talking about. And we'll talk more about this idea of a symmetric bell shape. And, you know, just like shapes of animals and shapes of flowers, there's tons of different shapes out there. Some of them have names and some of them don't. So let's look at another one. If I go back to, my Zoom screen is being funky. Let's try that down there. The 75% free throw, it is possible to get none, 1, 2, or 3 out of 12 in, but more likely the person throwing the free throws at 75% for one shot is going to be in this region over here. So I just want to draw on that. So kind of squinting at this one and drawing a smooth curve through this here. It's pretty low over here, maybe not that low. And then it starts to rise up, right? Up, 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 up. And then it peaks and then it comes back down. It's unlikely something would happen over here, but it could. Since this one right here has a left-sided tail compared to the rest. Excuse me a sec. All right, can you hear me there again? Since this one has a left tail, we would say this distribution is skewed left. The skew is to the tail, not to the bulk of the data. Add another. Let's see. Distributions could be what we call bimodal, where they have two peaks. So this distribution right here is symmetric, but it's kind of an upside down bell shape here, but it is symmetric. So things can be symmetric and not bell shaped. Bell shape is this kind of graph here. Here's another one. Think about the ages people get a hip replacement. Most likely they're going to be in their 60s, 70s, or 80s for a hip replacement. It's pretty rare that a young person needs a hip replacement. What would we say about the skew of this distribution? Anybody? Left skew, right skew, neither. Oh, did you guys fall asleep again?
It's in the chat, Gary. We said skewed right.
Oh shit, there it is. Sorry, I forgot my phone was there. No, this would be skewed left. The tail here is on the left side. So imagine that this thing is an animal, right? Here's its back here. This would be its tail. So this is skewed left. The skew is always to the tail. All right, let's try another one. Commute times for people to go to work. Typically people live close to their work. So if you ask people, how far do you drive to work? Mostly they're not going to drive very far, 1, 2, 3, 4 miles. There's a few people who drive farther, maybe 10 or 11, 15, or even 20 miles to get where they work. What's the skew on this one?
I believe it's skewed right, but we can't.
Yeah, there we go. This one is right because there's a right-hand tail. Yeah, skew is to the tail. So you look at the data and say, okay, do I see a tail here? Now, sometimes it's not obvious, but sometimes it is. So this one definitely has a left tail. Yeah, so this one would be, sorry, right tail.
Your bar chart.
What's that?
Your bar chart's not really showing up. We can only like really see like the numbers.
You don't see blue bars here?
Barely.
Oh, that's weird. What if we zoom in or I take a picture? Let me see. Close chat.
Just like
Oh, what the heck happened to my screen? Okay.
My computer? I don't know.
Nope, it's not your computer. Something went wrong with my screen. All right, let me see if I can fix it. We can leave that for now. I am going to close my notebook. I think that's the problem. Still black bar. Quit. Still a black bar. All right, stop sharing. Okay, so now you just see me. Let's try to share again. Share. Okay, do you see the whole screen now?
Yes.
Okay. All right, so like I said earlier, I usually project class from school, and doing it on my home computer needs a little work. I will fix that soon. Okay, can I get my whiteboard back? Looks okay so far, I think. Whiteboard, okay, I think I'm back to okay. Let me get my previous notes. Here we go. All right. And let's make a note of this. And just, this is super important. I have a hard time with left and right, and I get the two mixed up all the time. So the important thing to note for me to remember this is the skew is the tail. So you identify where the tail is, tail's on the right side, that must be the skew. So on this graph right here, this has a right tail, right with my right hand, yep, that's the right side. So right tail in the graph means right skew. So the main types of distributions we're going to concern ourselves with is it symmetric or not? Is it a bell shape or not? Is it skewed left or right? So just a summary of that. Come on. Oh, I have a new page. No, I have lots of new pages. There we go. So distributions we'll concern ourselves with. One, symmetry, symmetric. That is there a line you can draw where the left side and the right side match? So you get some kind of mirror image. Bell shape. Things can be symmetric with a bell shape and they can be skewed with a bell shape. Left skewed. Which means there's a tail on the left. Or right skewed. No particular order to these. These are just the main kind of categories we'll look at when we're describing what we see in the distribution. And the distribution is just the shape of the histogram. How do we describe it to somebody? All right, how are we doing on time here? Not too bad. Okay, so let's see, here's my outline of stuff. Talked about samples, we talked about skew, bell-shaped. All right, So next we have to actually look at some data. And I think I will take a look at the home prices that I had you guys playing with. And here I have the 2019 Pendleton and Hermiston. So a little review of the work we did last week. I'm gonna make a copy so as not to mess up this one.